problem. And this paper is called How Powerful Are Graph Neural Networks? It introduced the graph isomorphism network, the GNN network, that basically maximizes the expressiveness of any graph neural network. So something really cool about this paper that they discovered or introduced a formula where you can define a message update rule of the embedding that is highly or maximally expressive. Okay, so this is a different way. There are also like a family of other works that look at the expressiveness of the network from a different perspective. But let's have a look at what this paper has offered to the community. So here first, we'll start with, so the first thing is that they showed that GNNs are at most as powerful as a WL test in distinguishing graph structures. And they could be as powerful as this test. And also they define particular conditions on the neighbor aggregation, okay, the graph readout function. So the graph readout here, the word readout is what we called previously the prediction. Okay, so it's the final function that will output the label or the target score. And so here they basically define particular conditions on the neighbor aggregation and the graph readout function. So this aggregation function and the readout function, they need to have satisfied particular conditions. And under these conditions, the GNN becomes as powerful as the DUL test, which is really cool property to have. Now, the third thing is they also identified graph structures that cannot be distinguished by popular GNN variants. So, for example, the typical GCNN graph, Sage here, that use max function and also that use mean. So, using the max and the mean during the pooling, or the aggregation turns out not to be intuitive. And we have seen examples, actually, guys, previously. So we have seen here that these, using the max and the mean fails on different examples in distinguishing between different topologies. And this is also from the GNN paper. Okay. So now the last point they showed is that they developed, a neural network architecture or graph isomorphism network. So it's actually a simple update rule that they introduced. It's a layer that there are different layers that you can introduce in your network. So I'll explain this in a bit. But the idea is that we want to aggregate in an injective way. How can we do that? So let's update our aggregation and readout functions in this layer. And this is what they focus on. They updated these two components and by guaranteeing that they would be injective. Okay. So they show that this actually has a discriminative and representational power that is equal to the power of WL tests. And these are nice experiments in the paper. So I really encourage you guys to, kind of have an in-depth read of this paper and its methodology. So one important theorem in the paper, and I wanted to kind of spotlight this theorem because I found it very important and interesting. I think this is the crux of the paper. First, let's start with the let's go through this theorem 3. Okay, so let A be a GNN. So A basically defines our neural network. So we have a graph, and it takes in a graph and it maps it onto and outputs d-dimensional space. So A is our architecture, is our neural network. Okay, so that's the architecture or our neural network. It takes in the input graph. This is the input graph and outputs a d-dimensional vector. So here, with a sufficient number of GNN layers, A maps any graph G1 and G2 that the WL test of isomorph decides as non-isomorphic to different embeddings if the following conditions hold. Okay, so we need to satisfy these two conditions, all right, for our A network to, be able to map different graphs or non-isomorphic graphs, G1 and G2, which means that there are different, okay, so they're different graphs onto different embeddings. So this is a very important property that we want to satisfy. So what are these two conditions? Okay, so the first condition is that our network A aggregates, so there is an aggregation here that happens, aggregates and updates node features iteratively with. So this is the update, the node embed up rule. So we have seen different rules before, or message passing rules. Okay, so this is the update rule. And the update rule basically takes in two things. It takes the node itself, which is V here, and the neighbors, right? So the way we aggregate the neighbors. So F applies actually to the node, and then it transforms the node. So this is like in different models. So we take the nodes, we transform them, we aggregate them, so it aggregates the nodes. And then phi takes in the current node itself and the aggregated ones and applies a linear transformation. So have another transformation phi here, okay? So F aggregates, it operates on the neighbors, and phi operates on the concatenation of these two, or the integration of these two. So phi can take different forms, and F can take, of course, different forms. For example, for F, we have seen what did we say? So F could be, for example, max pooling. It could be summation, a sum. It could be also mean, right? Aggregation, etc. All right. Now phi is our linear transformation function that we want to learn. So basically what happens here is that first we want, both F and phi to be injective. So that's the main thing that you need to retain. So these two need to be injective, right? So if they are injective, it means in our function, in our update rule, right, mapping the previous embeddings of layer k minus 1 onto k to get the new embedding right here, the update of the embedding. Both functions are injective, so we're gonna aggregate in an injective way, which maximizes the expressiveness, right, of the network. So the second condition is that so the A's graph level readout, the final readout function that takes in, for example, all the HV for every single V in the graph, right, and transforms it into, for example, the H graph, or if we're doing a graph-based classification, right? So this function also, if you're using, I don't know, like whatever, previously we have seen max, also sum, we have seen mean, and other kinds of, like functions with attention mechanism and stuff like that. So these need to be injective. So the readout also needs to be an injective function. So everything is injective. So basically the middle layers are the aggregation, beginning and is injective. And the final one to do the transformation and get the output, the readout, the prediction score, or the class label, it should be vector too. All right. So now let's look at these different examples. So here we rank different, for example, we rank the sum, mean, max aggregators over a multiset. A multiset is actually a set where you have multiplicity, which means you have a bag of nodes, and in the bag of nodes you have you can have redundant nodes. Okay, so here, for example, we can see that we have a multiplicity of 4 for the blue one and a multiplicity of 2 of the pink one, which means the number of times these nodes appear in the multiset. Okay, so now we want to see which ones are more expressive. So the left panel, it shows the input multiset. Okay, so the network neighborhood to be aggregated. So this is the network neighborhood that we want to aggregate. So we basically, what happens in the paper, we all of these and we put them, we define a set. Okay, so now we have like a bag of nodes, every computational graphs, very simple. But in this nice example, what we want to look at is how different aggregations behave on this, computational graph now turned on into a multiset. Okay, so the next 3 panels illustrate the aspects of a multiset given the aggregator is able to capture. So the sum here is a summation, means you put everybody there, so add them all up, so everybody will contribute. Okay, so if you sum them up, so you can see that here the summation acts as a multiset. It preserves the power of everybody because you're summing all these embeddings right here. So if I'm going to put them vertically, So let's do some embeddings vertically. So these are my embeddings. If I sum them up, somehow I'm preserving everybody. Everybody will have a contribution with a multiplicity. So this guy will be repeated twice. These 4 embeddings will be repeated 4 times, right? So if we take color, we can change the color actually here to match this example. So we'll take blue. So here we'll have, 4 contributions, right? Now, if you do the mean, if I take the original input and I take the average, so what happens here, you're going to collapse, 2 onto 1 and 4 onto 2. So basically what you're going to have is like, you're going to capture the distribution. So mean actually gives you the distribution of points. And you can see in the distribution, for every 2 points, we have 1 pink. And here for every 2 actually points, we have 2 blues, because we do have a number of 4 there, so 2 times 2, right? So basically here, this gives us the mean distribution, and then the max distribution will remove the multiplicity. So we will find a set. So it acts as a set because we're going to take the maximum value, and taking the maximum value, it will shrink or reduce this set onto this. So aggregation using max acts as a set. Aggregation using mean, it kind of captures the distribution. And the aggregation using sum is a very nice thing to have because it actually preserves the whole computational graph, the whole multi-set. Okay, so here let's summarize this. So sum captures, so just a reword, so sum captures the full multi-set, mean captures the proportion distribution of elements in a given type, and max aggregators ignores multiplicity, so it reduces a simple set. All right, so that's what it actually looks at, because if you're going to look at the maximum of these, how many points? 1, 2, 3, 4, 5, 6 points. It boils down to actually looking at the max of these 2 because we have redundancy. So we don't care about redundancy in the max function, right? The multiplicity. All right. Now let's look at the summation here. Will the summation fix this problem, the sum? We didn't see it before. We didn't actually test this before. So here, going back to this example. So let's say, actually, maybe it's better to redo it here independently. We have space. So let's say we have 2 nodes. We have I and node J. And node I is connected to 2 other nodes, and J has 3 neighbors, okay? So each of these have identical, so we start with the same scenario. We have identical features. And now we're going to do the sum. So if we do the sum, now we're going to get these guys 3 times, let's call it embedding E, okay, 3 times E, right? And now what we're going to have here is 2 times E. So these will be different. So now sum here is actually very nice because in aggregation, it allows us to distinguish between these 2 topologies, as opposed to, for example, average. So if you take average or you take the max, where you're going to have it like exactly the same thing. So these 2 guys, so let me put it differently. Actually, here we're going to have this. So these 2 guys will map to the same actually embedding, right, with these 2 functions. And our functions are, as I mentioned, are here we can use the max or also the mean aggregation. So these are not good, right? However, the summation is actually good for aggregation. So here we have some nice insights into which kind of aggregation we should use, right? So now this is something really nice and a nice example in the paper, but now can we guarantee that the aggregation function here is actually intuitive? All right, so maybe we don't want to use only summation all the time. We want to use we want to have more variability and a complex mapping of our embedding. So if we use summation, it may work out nicely, but we may want to use more complex things and have, capture more complexity in these embeddings. So we may want to kind of, map them differently, not using a simple summation, right? So we can learn how to map them in a more complex nonlinear way compared to this simple summation right here. So the paper proposes that basically. So in the paper, the GNN paper, they showed that we can actually maximize. So this is the final takeaway from the paper. So how to maximize the expressiveness of a GNN model. Oops, let's do this. So we can use multi-layer perceptrons. So multi-layer perceptrons, they are universal function approximators, which is, a simple, convolutional, fully connected convolution neural networks. So simple. So it's like fully connected network with not the spatial convolutions. Just, we're learning how to do multiplications and summation. So it's a fully connected network, okay? And these fully connected networks, they turn out to be universal function approximators. So we can use them easily to model f and phi, all right? So these two functions that we want to have here, updatable, and also the readout function. So GNN basically is a maximally expressive GNN among others that may exist. And the GNN here, what it does, it uses MLP layers to do, like it adds it up to the transformation layer, the graph neural network layers. If you use GCN, you're going to top it up with an MLP. And somehow this MLP that you added right here, right, it will allow you to map injectively different inputs onto different outputs. So this will allow you to distinguish, like the neighbors, because now it's a very simple idea. Every time, instead of aggregating, somehow adding here an MLP layer, right, that will allow me, this MLP will depend on K, and this, MLP layer, this new mapping function that I introduced here, the MLP mapper, will allow me to distinguish these different topologies, all right, and map them differently. So this is something really nice, and basically this is what they have proven in the paper. If you read the paper, so they discovered that by expressing phi as MLPs, we can guarantee the expressiveness and the injectivity of the aggregation function that we have right here. So when we aggregate, we actually take, so this is the neighbors, right? We take the neighbors here, we have seen before. This is the self. You can actually set epsilon to 0. So they look at different cases where they actually remove this term, and sometimes it moves, other times it doesn't. But just in a nutshell, what we have here, we have aggregation, neighbor aggregation. All that we do is that we replace, instead of using a simple max or mean, or what else did you see, guys? The sum, right, which was better than the others. We replace these with an MLP, and by doing so, we can guarantee that we'll have basically this nice expressiveness, okay? So an expressive GNN block can take the following form. So you can add an MLP before your conventional GNN layers. So for example, node classification or post layers, you can do both, combine both. And this is something to kind of, experience with and try and see, what kind of behaviors you will get in terms of mapping different isomorphic, isomorphic graphs with different, with identical embeddings, and see whether we can distinguish that with these functions. And the paper goes through like kind of overviews a big set of, a large set of experiments, and you can have a read at that. I think you will master deeply, like the details of that, of this whole GNN architecture, but the idea is actually very simple. So instead of simply using, well, what we have used before, guys, so just take the message to take away is that instead of using a fixed, a predefined, so that's what they do, instead of using a predefined, a fixed aggregation function or pooling function, or pooling function, they make it learnable. All right, so it becomes learnable. Now, the bad news with that is they're increasing. So even when it becomes learnable, So it kind of, these layers, they may be, they increase, they require more computational budget. So this increases, these layer may increase the compute budget for the network, because instead of using simply defined aggregation functions, we are learning them. Okay, cool. So that was the GNN, and I think towards the end of this, it would be wonderful, guys, if you can take a few minutes, remember how to define node invariance mathematically and intuitively, run it on a few examples, node equivariances in GNNs, and also expressiveness. What does it mean to have a highly expressive GNN, and how can we guarantee that? What is the key idea here? Okay, thank you.